stop for an hour.
Oh, you'll absolutely get them. All right, so let's get started. Thank you all for joining us today. Our colloquium speaker is Dr. Todd Lauer from the National Optical and Infrared Laboratory, formerly known as NOAO. Todd didn't start at NOAO. He spent a great amount of time at Space Telescope, doing things like software corrections to Hubble images with WIFPIC 1 and 2, when Hubble, of course, launched with misfigured optics. Um, Todd is also part of the Event Horizon team, which you have seen the beautiful image of the black hole at M87 from last year. But he's also a member of the New Horizons team, which he'll be telling us all about today. And the particularly fun fact that I like about this is that Todd led the cheer time to We Will Rock You to Brian May during the flyby of Pluto, after the flyby of Pluto. So the entire New Horizons team started this cheer to Brian May, who was in the team at the time, and Todd was the person who actually started the entire process. Uh, so, uh, who can get more famous than that? With that, take it away, Todd.
Well, I don't know if I can top Brian May, but that was fun. And my joke there, this is I'm part of two Horizons projects, both New Horizons and the Event Horizon telescope. So I should start with a caveat that this will probably be a little bit of a different talk. I am not by training a planetary scientist. I have tried to learn while being on the New Horizons team. I came into the team for technical support for a variety of things, but it's been very new to me, and I've been trying to pick up planetary science along the way. Um, so what I have here is this will be sort of mainly a show and tell. Lots of pictures. I will give, I hope, some of the science background into this. Um, I will stop the PowerPoint at various times to bring up some richer material. So we'll see how this goes. And as we were just talking about, so I'm going to be yelling into my laptop for the next hour. And so please interrupt me. Just first of all, so I know that you're all still there. And, second of all, you may have questions or things you'd like to understand as I'm going along, and I don't want to roll over anybody. So please do feel free to interact. You may have to yell a little bit because I know Zoom, it's hard to get the speaker's attention, where it's a colloquium, you just shine a laser pointer on the speaker and say, yo, so, um, so I think the first thing I want to talk about is this is done in collaboration with the New Horizons team. And you always have to name your collaborators, although with 100 people here, that would take the rest of my talk. But this is the New Horizons team at Johns Hopkins APL Advanced Physics Laboratory in Laurel, Maryland, where the mission is run out of. And this was taken a few weeks or a month or so after the Pluto encounter, which took place in the summer of 2015. I will call out a few people, though. Right there at the center, third from the left, is Alan Stern, who is the PI for New Horizons. To his right is Hal Weaver, who's a project scientist, and he was the one I wrote a random email to 7 years ago asking stupid questions that got me involved with the thing. I'm off there on the right myself, in the thundering horde behind them. Second from the left is a remarkable individual, Alice Bowman, who is the mission's operation manager, although we just call her Mom. She calls herself Mom. And she's equivalent, for Star Trek fans, she's equivalent to the Project Scotty. She is the lead operator, lead engineer for the instrument. She's the one who actually has custody of New Horizons. They don't trust scientists and engineers with it directly. You have to go through, the mission control. And Alice Bowman is the one that actually keeps the spacecraft operating and working. And then to the left is Glenn Fountain, who's, of course, you always have to have a good project manager, but it's a great group of people. I didn't know any of them except just, one or two people in the most vague level when I joined. So this was an experience for me. They are, however, the best team I've worked with, and it's been a delight to work with them. So I want to give credit to all the people that made this mission fly. So Pluto was discovered now 90 years ago, just a little dot discovered by Clyde Tombaugh by blinking plates. And you can see the two arrows there, which would provide the Clyde Tombaugh so I could find it. But that's, growing up myself, that's all we knew about Pluto was this little point of light that moved back and forth. And even its diameter was up for grabs. It was kind of this leftover thing, you had the terrestrial planets and the gas giants, and then this little bit of whatever it is out there, which was like, what's that all about? So a little bit of context. Pluto, in some sense, can be called a double planet. It has a satellite which is half of its size, half of its diameter, an eighth of its mass, and that's Charon. The Charon orbits Pluto synchronously. You could make a rope ladder between the two and walk between them, for just pulling one hand over the other. For scale, and this is to scale, there's the Earth, and that's both the distance between Pluto and Charon and their diameters relative to the Earth. So Pluto is ballpark about half the size of the moon. This is the best that we had going in to New Horizons, to the encounter. This is Mark Bowie's work, who's on the team. And this is very clever reconstruction using Space Telescope and a now sadly defunct high resolution channel of the ACS instrument. Pluto is only a few pixels across in Space Telescope. Mark did some fabulous work of putting together several images. And right now it looks like a bunch of blobs, which it is. You see a bright blob going past there. It turns out that these blobs were surprisingly accurate. And there is one very big lesson from this, is that we did know that Pluto presented a highly variable surface. It wasn't a cue ball. It wasn't just a white icy ball or something, grayed out like the moon. It had strong contrast areas. We didn't know what these were. Again, you see this white thing or bright yellow thing going past. It was decided to phase the encounter to encounter that object, whatever it was, the brightest part of Pluto, and that paid off with some really interesting results. But you placed a bet based on this blurry image. Where are we gonna target Pluto? We're gonna target for what's coming around right now. So here are coming up with a dramatic fade are our two best color renditions of Pluto and Charon way after New Horizons. And Charon is about half the albedo, so this is a good relative brightness. The colors are pushed a little bit. Pluto is, white with some brownish coatings on it, and we'll go into this in some detail. This is the summary slide, and so here is where the ideas that I want you to take with you. I truly didn't know what I was going to see when I was coming in here, but it was striking to me that you could call Pluto a cryoworld. And it's actually a very rich, varied world with a lot of stuff going on. And I think I expected some, dead piece of ice, and it's not true. It's a very different thing. For example, water acts as basalt. A large part of the body is made of frozen water, but at the temperatures, which is 40 degrees Kelvin, it's rock hard, literally rock hard. And so that forms the geology, as it were. Nitrogen is largely frozen, but it acts as water does on our planet. That is, you have different phases, and those phases come up in various ways. It has an atmosphere. It is a vacuum by our standards, but yet, only at 10 to the minus 5 ours, which is actually fairly substantial, is variable. It serves as an important role in transporting materials, shaping the surface, coloring it, gathering it, coating it. And the planet is geologically active with highly varied terrain. And that I didn't expect. It's like, it's frozen, yes, but things go on at those temperatures with the different materials. And that was a surprise. Charon is more, I think, what I might have expected to have seen. Charon has no atmospheres and is presently inactive. And that the difference in mass is what made those two worlds different. Retaining atmosphere, retaining activity, Pluto was big enough, Charon was not. This I mentioned, they have synchronous orbit and rotation, and there are 4 minor satellites to go with them. There are no rings, although we look very hard for them. The atmosphere is made dominantly of gaseous nitrogen with a good fraction of methane. Is well known from Titan and other bodies in the solar system. You start out with nitrogen and methane, and you add ultraviolet that cracks and it makes more complex chemicals, nitriles, polycarbonates, hydrocarbons, and you make haze with that and material that drops out and colors the surface. And as I mentioned before, the atmosphere is sufficient to transport material. It creates nitrogen glaciers and frosts the mountain with methane frosting. Pluto is big enough that radiogenic heating actually gets up to supports very high temperatures in the center. We currently believe from a variety of lines of evidence that Pluto has a subsurface water ocean. Also, what you're looking at, which I will show further, is that there's a basin where you have convection going on of frozen nitrogen. That's Sputnik Planitia, and that is a unique feature. There's also cryovolcanoes, volcanoes which were built up with material coming up from the ocean. I won't get into this very much. Pluto is tipped over. It points the pole points only 30 degrees away from the sun. The orbit is eccentric. The pole precesses, the orbit precesses, and this is very strong, creates very strong seasons, and over million-year scales, very strong climate variations, and a Plutonian analog with the Milankovitch cycles that we have on Earth. So here's New Horizons. This is before its launch in 2006. It's down at Cape Canaveral. The usual phrase is they say it's grand piano size, which I think is about right. It's even a little piano shaped if you take off the dish antenna, sort of a little triangular. I won't be exhaustive about this. You have a variety of instruments. The ones which I have focused on are the cameras, Lauer, which high resolution panoramic imager. Then there is MVIC, or part of the Ralph instrument, which is a panoramic camera. So there are 2 cameras, but we have ultraviolet, near infrared spectroscopy and imaging as well. The dish serves as a radio experiment. And we have experiments to do particle physics and other things of the environment going out there. We even have a dust counter, to look for direct impacts. So a lot is packed in there. And then you see they're off at about 2 o'clock is an RTG. This is powered by plutonium-238, good for decades of power. It was launched in 2006 on an Atlas booster from Cape Canaveral, January 2006. I think they probably asked those people to get a little further away than when they launched. See, this is the path out. The inner solar system is just that blue blob in there, the terrestrial planets. It aimed for Jupiter. It got out to Jupiter very quickly. The ejection was at the time the highest velocity out of off the Earth. He went by Jupiter for a swing by, which was in 2007, and then a long cruise out to Pluto lasting eight years. The spacecraft was moving past Pluto at 14 kilometers a second, so everything happened very, very quickly. And then at the end, and I hope I won't step over the time too badly, we went and saw another object, Arakoth, a Kuiper Belt object. Its discovery designation was there, 2014 MU69. There's Jupiter. There's the encounter geometry, and this was immensely clever. This took a lot of work to design, and this happened before I joined the team. I only joined, I should say that my involvement started 2 years before the encounter. So this was 7 years in cruise by the time that I started bothering the team. So this, you see the sun there, the system of satellites and Pluto is almost face on to the sun. The Earth is only a very small angle away. We're out at this point, 33 AUs. So an astronomical unit is only a couple degrees. So the Earth is very close to the sun as seen with New Horizons. And, those things there are intervals in hours. So you can see that most of all this hard work goes down to, maybe 6 hours of close encounter. And it's phased to do a few things. I mean, you want to see Charon as well. You want to see the minor satellites. You want to look at the sunlight as it goes through Pluto's atmosphere and is occulted by both of them. You want to measure the spectra as you do that. So you have to go through the occultation zones, and you want to do that with radio from the Earth. One of the things I got a kick out of was they used Arecibo to send a huge whopping slug of radio photons off to the spacecraft in time for the encounter. And I remember this, you would work this out. It takes 5.5 hours at the time to get out to Pluto. And the team would say, well, we've sent the radio blast on this particular time, and that was like hours before the encounter took place because it had to, the photons had to get there at the right time to be seen by New Horizons. This is looking down, this is Space Telescope at the system. Charon was discovered ground-based observations in the late 70s. The 4 minor satellites were discovered by Space Telescope, 2 of them after New Horizons launched. And this is a story, and this is in a sense how I got involved. You're flying a spacecraft which costs the better part of $1 billion into an unknown and hostile environment. You knew that there are 2 minor moons when you're there. Space Telescope picks up a couple more. So what exactly are you flying into? And is it safe? And this is what got kicked around at the start of the last decade. Do these guys know what they're doing? And they spent a huge effort on a hazard investigation. And this is where I was reading about this and I didn't understand, what they were doing. And, I got involved with them. And this is this slide. This is my first contact with the project. This is most of the original hazard team. You see Alice Bowman, who is not on a team, but we're happy for her to be in the middle of this. That's her domain. The control room back there is in the middle. John Spencer, an immensely capable member of the science team in the orange shirt, is right behind her. He was the leader of the team. And the bulk of the team was sort of traditional planetary astronomers, in the interface between regular observational astronomy and a deeper planetary science. And there's a whole spectrum of scientists on the team, all the way from rockhounds at one side and then extragalactic astronomers on the other, like myself. And this was the Enterprise. So Pluto very conveniently was located at the center of the galaxy, the richest star field, in the whole sky. And there you see Pluto and Charon blurred together. And this is New Horizons data. And your problem here is against a rich crowd field, which is tremendously undersampled by the camera, and the point spread function varies with every exposure. Find unknown satellites and unknown rings in this mess. And that was what I thought was an interesting challenge. My own solution, for those of you who are familiar with data methods, is to use principal components analysis, which can take this off perfectly. And I never even bothered to identify stars. So there's no stellar photometry, Dolfo, Dufo, or the OFOT, or any of that stuff that people use for crowd field photometry. This is just global principal components analysis to an ensemble of images, but it takes things off very, very well. And so going into this, we spent a few months of recording into Pluto. We found no new satellites. We did find all the old satellites, and this is a mosaic made from New Horizons images. And you can see motions there. The little dipoles are a few hours apart, and there's Styx, Nix, Hydra, and Kerberos. Charon closer in, some artifacts, but we found it safe to go. And then 2 weeks out, we gave the all clear and went out to a local pub to celebrate the all clear. And this was a very elaborate thing. The all clear was we had 5 trajectories. If we found something, we had some alternative paths, which we could have flown by Pluto at the sacrifice of science, and they weren't necessary. During closest approach, the spacecraft does not have a scan platform, and so it moves the spacecraft, and so we go out at radio contact during the business end of the encounter, and then you hope that it survives to the other side. And my joke was that, being there at APL in the crowded auditorium and all of us waiting to get the signal back, that we should have had a getaway car with the engine running just in case we were wrong, that was safe to go through Pluto. But fortunately, that escape was not necessary. It survived. And this is going to be a montage of getting close to Pluto. And this is some of the other stuff that I did with the team, which was to take the images and weave out high resolution images. This is a week out. And Pluto's rotation is about 6 days. And so over the course of a week, we'll get one rotation and we're going to end up in about the same place. And so here you can see we've gone from a fuzzy blob to finer fuzzy blobs, which is intriguing. And this was fun because the astronomers, like myself on the team, got all very excited by the fuzzy blobs, whereas the geologists sat there, or the planetary geologists, with their hands in their pockets. And I heard one of them say, no, it's not geology yet. But we watched this from basically hour to hour, day to day, and getting in closer, and the blobs turn into more enigmatic markings. And maybe you start to see some big craters. And what are those fine things over there like channels? And about this point, the geologists just turned on full power. And it was spectacular because I didn't know what I'm looking at, but they were just all over this. And so click, 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 looked at dark areas that we saw in Space Telescope is now all chopped up again. And now you can see something that very frankly looks like a crater over there, a target almost. And we're going to bring that around. And now you can see some enigmatic channeling, rifts, perhaps valleys on the top. The North Pole is at the top, by the way, and we're rotating around the pole here. And then we come back, and then we're back to this basin, Sputnik Planitia. And we'll just click this a little bit more. And then we had color from one of the panoramic cameras. And this is about how Pluto would look to the eye. These things cooked up by the haze atmosphere. I think I was born in Akron, Ohio, where they vulcanized rubbers, and vulcanized rubber and made tires. And I remember the pollution at the time. And I suspect this is very much like Akron, Ohio, raining down on Pluto. So this goes back to my childhood from a factory town. So I'm going to stop here, and I'm going to show some better materials on this. And let's see if I can. Oh, I guess I can just go right here. Yeah, is that going to work? Okay, now let's stop share. Let's try this again. This would be a good time to ask questions, by the way, if any. Okay, there we go. No, I don't want that. Let's try this again. This, I apologize. I did not practice this part. Let's do that.
You're sharing Pluto mvic bestcolor.png. That's what you.
Okay, so do you just see that, Gotham?
Yes, I do.
Okay, let me enter full screen here. Okay, so this is our best full disk color image, and let me just see if I can zoom in. Yes, good. Okay, this image is a little better than it appears. Is actually 8K by 8K, and so I can zoom into this with tremendous resolution. And so here is, and if any of you get motion sick from this, speak up before I hear barfing over I don't want to get people motion sick. So this is tremendous. This is the sea of frozen nitrogen, which is slowly convecting. And you can see these polygons throughout here, and these are convection cells. You go up here, and there's different colorants. Is mainly very slushy frozen nitrogen, very soft frozen nitrogen, dusted with carbon monoxide, methanol, and methane. And I know if I add into this, there's a little bit of hydrogen cyanide dusting everything. So not a place where you want to walk around, or at least you want to clean your boots off before going back into the airlock. And you can see there's an interesting thing. If I just zoom in to some of these places, you can see what look like flow patterns, sort of swirling coffee. If I go over here, there's evidence of glaciers. I have better material, which will show this later on, coming from highland channels flowing this sea. There is nothing else in the solar system like this. In nitrogen, slushy nitrogen, ice, water ice, floats in the nitrogen. And so these are really icebergs. These appear to be wind streaks. We called this the Klingon starship, with, I guess, impulse drive coming out behind it. But we think those are wind streaks. There is this red material. These are probably tholins. These are stuff cooked up and drop out of the atmosphere in what looks like shattered crust here. And so this is a place where at the edge of the basin, the crust broke up to make these blocks. But there's something else that, the things that you don't see. And here's a few examples. There's a crater. But you notice that you haven't seen any of these craters over here, none at all. And we've looked very hard for this in the sea. And so this means a very young surface. Even here, where there are large craters, there's not a lot of fine craters. This has clearly been processed. So we go into the highlands. You see these interesting channels, which may have been carved out by glaciers. There's one feature up here, which drives me crazy, if I can find it. This is like being a tour guide, sort of an alien land. And it's sort of funny that I have this map of Pluto in my memory, so I can say, well, let's go over here, let's walk over here, see that. It's like a tour of a national park. There is a channel of some sort. There were 40 degrees, so you tell me what made the channel. It wasn't water ice. And of course, right now there's very little atmosphere. The idea may have been with the climate cycles that Pluto may have had a thicker atmosphere at some point that could have supported liquid nitrogen, or that at a different epoch, nitrogen ice built up, and at the base of the ice, you had enough pressure that you could support an underlying liquid nitrogen layer, which perhaps carved things, or perhaps this was just done by a glacier, but that looks like something that flowed. And if I go over here, there's this weird sort of dendritic network, again, suggestive of something that has been flowing on the surface. Let's zoom out. Yes, here's more of this, even better. There's a ridge line, and this is interesting. Pluto has what's called extensional fractures. And let's see if I can see this a little bit. Yeah, there is, if you look here, you can sort of see it tracing all the way across. There is this rift, which looks like Pluto has actually swollen up a little bit. And that's probably as the water ice has frozen and the ocean underneath has retracted a bit and contributed to an ice crust, and you have faults. Ice expands as it freezes, and this is what's going on here. Again, a rift zone here, which is where really clearly this, I guess, is called the graben, where this is dropped underneath. And again, this is due to expansion. And this area here was very useful for us because we were able to get examples, or compositional examples, of what we think came out of the ocean. Likewise down here, these are expansion rifts. This is what you might expect to see in an ancient body. This is a classic sort of heavily cratered ancient terrain, but clearly this does not dominate Pluto. The rest, you go from here to right over here, the surface is very young. And then we'll walk across. This is something we still don't understand, some very deep pits. This is not a crater. What created this is still a mystery. This is the highest area in Pluto. These are mountains, and you see it's covered with these interesting ridges. We call this bladed terrain. We think this is methane ice, which has gathered on the surface of Pluto. And over time, the sun has caused it to sublimate and make these features, which on the Earth, on a very small scale, are called penitentes, and I will show them to you. This is something I love to see. If you can imagine being on Pluto, in the middle of this mountain range, there's this flat valley, and you see there are shadows here. And if you could picture being there, looking at the distant sun, you see these shadows are very, very jagged. And so imagine looking at Pluto through these mountains, which have almost vertical features on the gigantic scale. There's no Earth analog. I was just thinking in Tucson, we have Finger Rock up in the Catalinas, which is a vertical rock that's quite big, but these dwarf anything we have. And you can look around. Yeah, here's another little valley with the same thing going on. Let's walk across over here. Let me zoom out. Let's go down to the south. And then there's this other interesting feature right here, which I will show you more later. This is an elevated peak with a deep pit inside. It's not a crater. This is one of 2 or 3 candidates that we have for a cryovolcano. We've given a lot of attention trying to understand what is going on in this feature. So active geology, and you can see just from place to place, it's not the same thing. I'm going to show you now the highest resolution strip that we took, and I think I'm still doing okay with time here. Yeah, let's bring this up. And let's see, full screen, right, okay. So I'm going to zoom in on this. So the way New Horizons work is we have this panoramic push broom camera, which is basically a one-dimensional camera, and it sweeps across the surface of Pluto with spacecraft rotation. It has color filters. So we actually have 4 cameras, one-dimensional, which sweep across the surface. And this is a standard trick used in spacecraft for panoramic imaging. But in the middle of this, as with Space Telescope that has parallel instruments, we have a high resolution monochrome camera, and that's the one I mainly work with. And that gives us the best resolution. And so we're just going to walk across this strip. And you see there are craters that have been buried by ice deposits, with layers being sampled. There's this washboard kind of texture, not dunes. We don't think it's dunes, but we think this is sort of like a corrugated, eroded dirt road that you see, around. made by wear, and we think this is the action of glaciers over time. So we're going to head down to the sea, and this is where the 3D pictures are going to come in a bit. There is tremendous topography. Where I have my cursor, there is a 2-kilometer cliff along this line. You can't see this in a single image, but there is an incredibly deep valley there. We go into the broken crust, and then we hit the polygons, and clearly there's some kind of landslide that has come into here in a few places. This is one place where we think there are dune fields, that material is being blown around by the weak atmosphere. But this turns into the polygonal cells and the pitting on the cells. We think this is the action of the sun causing the surface of the ocean to sublimate. And you can see signs of a convection, that these are smooth in the center. So there's upwelling in the center and goes down towards these boundaries where it's subducted into the ocean below. And this continues for a while, and there is no other analog anywhere in the solar system that looks like this. And if you go far enough south, the convection eventually stops, and that's probably because the ocean shallows out. We think at its deepest point, it's about 10 kilometers deep of frozen nitrogen. But here it's shallower, probably less than a kilometer deep. So the cells are smaller, and then this turns into what we call evocative, at least sandpaper terrain. Still sublimation, but irregular. And then we have these large pits, which reminded us of bacteria. Although I know I didn't fool real biologists with this, but to astronomers and geologists, they look like bacteria. And again, the best idea that all these are sublimation, and here there's no convection, but it's still a question, why is this so free of any detail over here, although there's some ghosting of features over here, but then this sort of very stippled surface, and this continues into now the start of the highlands, and then this goes up to the cryovolcano, which is not in this particular scan. So I think with this, I'm going to resume my presentation. Let's see. Right, okay. Let's see, yes. And this is time for 3D glasses. So is everybody with me? If you don't have 3D glasses, this is not going to go on very long, so I ask you to sort of grin and bear it. This is the New Horizons geology team in Texas of a few years ago, and this is two people got up with their iPhones side by side and took this picture. I'm sitting in the middle there behind the slide projector, but you want to have your red lens over your left eye and your blue on your right. And so if you can see this in 3D, this is a good calibration. And let's get to real Pluto. And this is a strip of Sputnik Planitia going into the highlands. And give yourself a little time to sort of register around, but I draw your attention to Rise, Mons Rise, right Mons, which is the cryovolcano in the right end of the picture, and you can see that that rises very starkly above the plain. You see ice mountains, but you also see how flat it is in the sort of shore of Sputnik Planitia. Gotham, is that working for you? I
Yes.
guess, okay, perfect. I'm going to go on. Again, and anyone interrupt if you're having troubles or questions before I. go on too much. This are two separate scans across Sputnik Planitia. Now you may remember that I talked about these deep valleys, and here you can see it in 3D. And I should say, by the way, that this is something very deliberately planned. The planetary geologists on the team were quite insistent on, planning the encounter to get depth imaging. And this has been incredibly useful for us to understand the geology. And so we know, for example, the depth of the basin. You can see these ice mountains, which again, a lot of relief, several kilometers worth of relief, but also this very deep pit at the edge. And you can see that right at the bottom there. And that's where I drew your attention. With the single scan, you really don't see this, but you put a couple of them together and it just comes up. Here are the highlands I talked about with the bladed terrain, the sublimating nitrogen. Here you can see the depth of this rift between them, but also the height of the mountains. And I mentioned, I drew your attention to the valleys, and you can see, looking up at the upper left, one of these valleys or depressed areas right between the mountains. Charon, I'm not going to talk much about, but we did as much on Charon as nearly as much on Charon we did in Pluto. This is interesting. This probably froze solid. We are not sure that it has liquid water underneath, but as it froze solid, it expanded and the crust broke up, and you can see these blocks of crustal material. And you can see again the great relief on Charon, and you can also see a pit at the top there, which is very smooth, where this material coming up probably was ammonia water, which is very viscous. And so it does not flow like regular water does, and creates sort of very ropey, thick features on the surface. And I think, yeah, that is the end of the glasses. And this all goes to producing a elevation map of Pluto. And there you can see, the basin, there's the scale on the left to calibrate you. We got a throw of 8 kilometers up and down in depth here, and this is quite depressed, the surrounding terrain. So between here and there, that's 8 kilometers. That's quite a bit of relief in a very small world. But this is flat. You can see that the edges are elevated. So it's clearly what we think is this is an impact basin formed early on in Pluto's history, and it made a cold trap, which was evacuated, but then very quickly was filled with frozen nitrogen. This is a diagram. This is produced by Francis Nemo, who is on the team. And this is a thermal history of Pluto that's years, or rather millions of years at the bottom. So that's a billion years where I have the cursor. And you can see that from the formation of Pluto, it took time for radiogenic heating to come up. This is a depth going up from the center to the surface. And there is this line, at least with Francis's predictions, there's the water melt point, or ice melt point, 273 degrees Kelvin. And so with this particular modeling and the expected amount of heat, Pluto has a rocky core with ice underneath, on top of it, that there is enough heat from radiogenic decay to produce an ocean. This is a current best by model of what it looks like: silicate core, liquid water ocean, ice crust, and then here is Sputnik Planitia with the ejecta blanket around it. You can remember you saw that this elevated ridge around it, and then here's these broken pieces of crust. I want to highlight James Keane, who is the artist who drew this. He's actually, I shouldn't say artist, he is a planetary scientist. He's a postdoc at Caltech now, and a member of our team, a very gifted scientist, but he is an excellent illustrator, and I love using his stuff. And this is his diagram of Sputnik Planitia, which explicitly shows the convection that we see. So subduction here going down, upwelling is in red. This is a process we think probably takes about 100,000 years. So it's a very stately process. The motion is like plate tectonics on Earth, only a few centimeters in a year, but you add it up over time, you have spreading. And so the surface is very new. And again, we have not seen any craters at all despite looking for it, but that gives us probably a limit of only a few million years. But a few million years now is essentially right now. This is a little image processing that I did on the mosaic. You can see the smooth areas in the center, and this is just a little filter which responded to the local texture, and black is smooth, white is rough, and you can see how this corresponds. A very quick way to visualize where the spreading is taking place. Let's see, let's match. Yeah, this center right here, you see it's smooth. It upwells here where it's black. Over time, again, thousands of years, the pitting from the solar sublimation increases. And it's a wonderful pattern. One of the interesting things is that Sputnik Planitia actually supports the idea of an ocean, and there's lots of evidence besides the theory. Sputnik Planitia is exactly opposite from Charon. Charon hangs in the hemisphere opposite our encounter hemisphere. So if you were in the middle of the sea, you would not see Charon. But the question is, why is this there? And tides will give you a mass anomaly such that a high mass area wants to be away from Charon. And the only way to get this to work, because the basin's evacuated and it's filled with nitrogen, which is less dense with ice, so that's a negative mass anomaly, which should be underneath Charon instead of the opposite side. So how do you do that? Well, so you've evacuated a large part of the crust when you made this, and this causes the ocean to bow up, and the water there is very dense. And so just by natural geology, how the planet responds to the formation of this basin, it pushes back, the ocean upwells, and you integrate over this, you actually get a positive mass anomaly. And so this is putting the pieces together to support a liquid ocean. This is what I talked about a little earlier. This is an elevation map again, but here you can see explicit signs of glaciers coming down from the highlands and flowing out into the ocean. And here, this is a regular monochrome picture showing the flow. This is just that. This is pure elevation. This is pure albedo. And we see this in a lot of places. And so this is where this thin atmosphere really comes in. It actually condenses out. There's cycles where sublimation is more important. You can build up the glaciers, and these will roll into the ocean. Right now, we're at a time where the glaciers are greatly subdued, but we think this is something that changes back and forth over millions of years as the pole and orbit precess. And I don't think this is more of the same. I won't talk too much, except that we see debris as glaciers do, a lot of stuff being transported into the ocean. We think these are blocks of water ice, which are literally icebergs floating in the nitrogen sea. And the bladed terrain, which I talked about, and I will skip over that. And these are these penitentes on a much smaller scale, given the picture of the person in the middle there. But we think this, these are on Earth, the sun eroding a snowfield. And we think this is exactly the same thing going on here, except longer times, thicker ice and methane instead of water ice. And let's see, how am I doing for time? Yeah, I still have some time to play. This is looking back on the dark side of Pluto, flying away, and there's forward scattering from the haze in the atmosphere. The color is genuine. It's actually blue. And you can see this from a long way out. And I want to show you a fabulous version of this. So let's do share screen once again. And what do I want to bring up next? Okay, do I see? Funny, I am not seeing what I expected to see. So I'm going to rummage on my Let's see. Yeah, something is missing here. So I'm going to end, let's see what I want to do. Let's end show. And pardon me because I do want to show this. Let's see. Oh, here we go. Okay, I don't know why this was not visible, but let's bring this up. Oh, I guess I'm talking to my screen. You can't see what I'm doing here. So it's okay.
There you go.
Okay. So there, this is with the panoramic camera looking back. And again, this is a deceptive image because it needs a little zooming up. And I just love this thing. When I saw this, I declared this as the coffee table image. You can see, yeah, let's go up here. Okay, this is not catching up, unfortunately. I've got myself gummed up here, so let's, I may not be able to show this. I think the problem is I've got a lot of stuff open, and I think that is, let me go over here and see what it's doing. Yeah, I think I'm going to waste your time here, so I think I'm just going to get on with the rest of this. It is a spectacular image, and I regret that I did not practice with it in advance. But let me get back to the presentation. And let's see here. Here, the PowerPoint, right. Okay. If there's time left over, I may try to play with that a little bit more. So one of the things we did get from the haze, which was wonderful, is we saw more of Pluto than we expected. Pluto actually is bathed in twilight, and we were able to get terrain in twilight and discovered 2 additional volcanoes in twilight imaging. Charon, I talked about. This is our best color image. The upper part is unique in the solar system. It has a red pole. We think this is organic material transported from Pluto, which is collects in the night on Charon and is basically processed by cosmic radiation to cosmic rays to higher polymers, which are able to stay put. And so this is a little painting going on from Pluto. The icy satellites, I won't talk too much about. This is Hydra, our best images of that. Nix, we think these are largely bits of pure ice chipped off at the collision. There's 2 images of Nix. We have craters on it, which again give us an age. This is a little bit more image processing. This is our best images of Kerberos, and this is just an advertisement for some of the tricks I do. The left are the images as they come out of Lauer, and the right is my reconstruction, putting several images together. Styx, we just know it's an elongated thing. We learned their diameters. And this is a departure picture, which is a long exposure. And I just love this for aesthetic reasons. We look back looking for rings, and so there's a purpose to this. This is a very deep exposure of the haze ring around Pluto. We see stars now on the opposite side because we're now looking away from the center of the Milky Way. And over here, there's Charon, and you see 2 things here. The sun is off at the bottom, and you see the crescent of direct solar illumination. Most of this is dark, but you see this shaded area here, and this is actual Pluto shine lighting up the dark side of Charon. And who would have thought? Well, the team thought, so they planned this image. But with Pluto shine, we've been able to study parts of Charon not accessible during the direct part of the encounter. We have some sequences which I have spent a long time digging into, which I'm writing up, where we do the opposite. We use the shine of Charon to light up the dark side of Pluto, but I don't have anything I can show today on that. So I want to spend the last little bit on Arakoth, and I have, according to your clock, 3 minutes, Gotham. So how do you feel about this? Should I just plow ahead?
Go ahead.
Okay. So this is less extensive, but we knew we wanted to see a Kuiper Belt object after Pluto, and so the team searched for it. Mark Bowie and John Spencer led this effort. They discovered an object that we could go to in 2014, hence the designation. And so Pluto is here. This is later on, but we flew past Pluto, applied various course changes to get to this object, which was completely unknown. I love this diagram of the outer solar system. 25 years ago, all we knew was that Pluto was out there, and that's it. So here is Jupiter, Saturn, Uranus, Neptune. Here's Pluto. All of this structure has been discovered in the last 2 decades. This is a new third zone of the solar system. This shows inclination plotted here versus semi-major axis. The objects are plotted where they are for semi-major axis. There is Eris, which rivals Pluto in size. There are resonances with Neptune. Pluto is in the 3-2 resonances, as several other objects are, appropriately called the Plutinos. MU69 is down here in a low inclination orbit, very far away, 44 astronomical units. And this is called the cold classical disk. We believe that these objects are truly unaltered from the start of the solar system and have not been altered by resonances or anything else. They are formed right where we see them. And so we were keen to get a look at this. We had another hazard effort. This was a hazard team was reconvened. This is a drawing of the hazard team by my oldest daughter, Sandra Muller, fitting around the New Horizons spacecraft. She gave her dad a laptop in the middle there, where other people were doing the hard work with binoculars. We showed this to Alan Stern, and he was not happy with Simon Porter hanging onto the RTG, which he said puts out about 4 kilowatts. So that would be a little toasty if you were there. And I think I'm going to show an approach video and see if this works better than my previous image did. And so let's share screen. Yes, let's bring this up. Okay, and let's see, enter full screen. Do you see this, Gotham?
I do indeed.
Okay, so this is an approach from the bridge of New Horizons to Arakoth. Again, we're looking at the heart of the Milky Way because we're going in the same direction as we went for Pluto. And you see Arakoth there right in the middle, picking it out from the stars as we get closer, starting to drift. These are real images from New Horizons, if not the real flight deck. You now see it rotating as we're able to resolve it. There you go. I should say that you see that I have this as my background. It went the other way around. I had a static picture as a background, and James Keane, in the middle of a telecon, snagged the image and pasted in the approach encounter and movie and into my screensaver and played it back for everybody all over the space of a telecon. I was deeply impressed. But let's talk a little bit about Arakoth. So it's bilobed, and this is interesting. To give you the scale, this is very, very small. It's about like one of those little icebergs in Sputnik, Planitia. The whole length of it is about 34 kilometers. It has what we call the head, which is a little more roundish, this flat body, a bright collar where we think material has collected. This is the lowest gravity point. Um, an ancient surface is very lightly cratered, but out in the Kuiper belt, we believe the collision rate, which we actually measured, well, not the collision rate, but we were able to use Pluto and Charon to calibrate what we think the collision rate is. This is consistent, again, with a body that is formed very early in the solar system. The bilobate structure was expected and is diagnostic. This gives you something perhaps more familiar. This is Arrokoth, as we now call it, compared to Phobos, about the same size, about the same reflectivity. That's very, very dark. The reflectivity is only about 12% or so. This is, again, we did stereo imaging, and not everybody can do this. This is 2 high resolution images. The best image is in the center. The image before the best image is to the left and right. It's the same image. You have choice. If you cross your eyes on the left, or can do parallel stereo viewing on the right, some people can do both. You can see it in 3D. And so I'll give you a second. If you want to simply try crossing your eyes, you can see Arrokoth popping out at you in 3 dimensions in the middle. And this, of course, again, is something we plan to be able to diagnose what's going on. Can you see that, Gotham? You're my witness here. I'm hearing not chatter from anybody else.
Oh, I know. I'm pretty sure you've taken everybody's breath away, but yes, I can more or less cross my eyes and look silly as well.
Okay, good, good. So this is the shape modeling, and what we've learned from this is, first of all, both lobes are flattened, they're co-aligned, and this is very important. And one thing we know is this has to be, and you would know this right away, this has to be a very gentle collision. They're brought together with a speed of less than a few meters a second. Otherwise, there would be disruption, flattening, everything else. And we've learned, or at least got great confirmation of the idea of how these objects formed. And what we have out there is a rotating cloud of pebbles formed early in the solar system. And this was when a lot of gas was still around, and there's a streaming instability as the particles move through gas, they clump together. The cloud has angular momentum, and you form naturally 2 condensed bodies which sweep up all the material and conserve the angular momentum. And in fact, one of the things which is common is that 50% of all the called classical Kuiper belt objects we've seen are binary objects. And so this is a very common feature. The trick then is, how do you bring them together? And Bill McKinnon, who is a geophysicist on the team, has a very intriguing idea. This happened early enough that there's still significant gas, even in the outer solar system, and there's a slow bit of gas drag that actually brought the bodies together. But you need something like that to make a very, very, very gentle collision. The one big thing that we don't know, and we looked and looked and looked for satellites, is anything that would give us a measure of the mass. A satellite orbit would have given us the mass right away. We don't have the mass, and they're too small to affect the trajectory of the spacecraft. We know that if the density is much larger than a half in CGS units, the gravity will actually start to deform the lobes together, and that very sharply defined neck will collapse and be filled in. But they're rotating together about 15 hours, and if the density is less than a quarter, they would actually fall apart. So we have arguments to give us a density of ballpark of half in the CGS units, but that's something that we'd very much like to know. So this is my penultimate slide. This is just in the geology room, which I was part of. There's my belly over here, looking at Arrokoth. The encounter was January 1st last year, 2019. And I just love this image because it was a great time of discovery. We'd worked very hard for this moment, and there were a lot of people here. The team was very good. Everybody in this picture worked very hard, and there's several dozen people not in the picture who also worked just as hard. And just all of us sort of staring at this image, and this is the first time we've seen it, was tremendous. We are continuing out into the galaxy, and I will leave this here. We have gotten far enough now that we can see the nearby stars actually move from where we see this on Earth. And this is something we did earlier this year. Two of the nearest stars, Proxima and Wolf 359, we imaged simultaneously from the Earth and New Horizons. The parallax is the better part of an arc minute. And this, by the way, is something that you can give your Astro 101 students. Rather than making diagrams, you can say parallax. We can show it directly now. The first time this has been done. And I've gone way over, and I will be glad to take questions.
First of all, let's thank Todd for a fun presentation. And yes, let's have any questions that you might have for him in the 8 or so minutes we have. Use the raise hand feature or just unmute and ask them.
Hi, I have a quick question. You mentioned the organics painting onto Charon. Can you say a little more about the ideas of the organic chemistry happening on Pluto itself, including the energy sources and in the solvents that are around?
Right. So I have a slide. I don't know if I'll bring it up, but you start with molecular nitrogen, N2, and methane, and that's what you have in Pluto's atmosphere. And the ultraviolet photons from the sun crack the methane. And so that makes radicals, which then look for something else. And you can build up very quickly higher hydrocarbons, ethane, propane, which we do see in our occultation spectrum. When we shown sunlight through Pluto's atmosphere, we look back and we're able to see higher organics. So you've got hydrocarbons forming. You can form cyclic hydrocarbons, benzenes, things of that sort. Now the carbon from the methane will combine with the nitrogens to make a cyanide radical, and that's the start of nitriles. And I'm not a chemist, so I can't describe it as much greater detail than that. That again gives you another tree to building more and more complex molecules. And as you do this, they have higher molecular weight, they have higher freezing temperatures, they become less volatile. In Pluto's atmosphere, they can make haze particles which actually fall out and coat the surface. In the case of Charon, we think it's most likely the lightest stuff, methane, ethane, what have you, going directly to Charon and being trapped in the night side with a cold trap. There, the temperature gets down to 20 degrees. And so you have a thin layer of ice. There you have Lyman alpha radiation, actually just from the background, and cosmic rays do the cracking. And during the nighttime, assemble more complex molecules, which again get above the point of evaporating when the sunlight comes back at the end of the night. And the nights last about 80 years as Pluto goes around the sun. Does that address what you're after?
Yeah, and it's a very similar process, I guess, what's happening on Titan, right?
Oh yes, Titan is a perfect analog, absolutely. It is very, very similar to Titan. Titan as well has the nitrogen and methane. That's a perfect analog,
Thanks.
absolutely.
And there are actually people who study this sort of stuff in the laboratory environment, like Sarah Horst, for example, right?
Sarah Horst is absolutely somebody who's been looking at this, and she's not a member of the team, but she has come to some of our meetings, and she's certainly been a resource for, I think, a number of people on the composition team, which is another sub-team on New Horizons, to understand what's going on. But yes, Sarah is a laboratory scientist. Will Grundy leads the composition team on New Horizons. He's also a laboratory scientist, and there's a lot of things we just simply don't know. I mean, the behavior of various mixtures of ethane, um, methane, what have you, at low temperatures, how they act, how they interact. A lot of this is unknown, and people put this together in the laboratory. I should also say one thing I forgot to leave out of the mixture, but yeah, carbon monoxide is also important. There you have oxygen molecules also helping out, and so that's also going on.
Let's see a question from Adrienne.
Hi, yeah. So I was reading about the bladed terrain a while ago, and it's methane and it's really sharp relief. And I think what I was reading is that we did not know until we looked at Pluto that methane could support structures like that there was a lot of questions on that. Can you speak on that if you know anything about it?
No, I can't. If I could summon up Will Grundy right now, he would be the perfect one to answer that. Yeah, your question is absolutely right. The fancy, and I keep learning these words. The word that I learned is rheology. The material properties of how these substances behave. It wasn't known, and so I think, and I was boning up for this talk, and I think what we have with methane is that you may get hundreds of kilometers. Now there's likely to be water ice mountains underneath of that gives you more relief, but to build up the blades, you do have to have a few hundred meters, and I think the thinking is that methane can support that. But you're right, that was an issue, and I can't tell you any more than that. And I would have a look. I know Jeff Moore has led this, and we have papers where I'm sure this is discussed, but I apologize that I can't answer your question myself.
We've got time for maybe one more question, then if you'd like to stick around and see if Todd can pull up that image of Pluto's atmosphere.
We'll try it. Yeah, we'll try it.
That's a question. I will.
Can I ask about that?
Hi, Brian.
I just wanted is it clear what sustains Pluto's atmosphere? Like why it doesn't just dissipate to the vacuum?
Oh, that's an excellent question, and this is at the limits of my abilities as a planetary scientist. I can send you to a paper by Randy Gladstone, which was our first. He was the atmosphere team, and that was in our science articles we published. Our first paper is out of the encounter, and that was published in 2016. I believe that it does not need to be replenished. I think, the temperatures are cold enough, and the nitrogen is heavy enough that it is able to endure in Pluto's gravity. Hydrogen, I think, does escape. Nitrogen, I think, does not escape. Methane, I think, sticks around. There is all the same some cycling. During the night, this will condense out. In fact, one of the things which was a little surprising to the team is that prior to the mission, it was felt that Pluto's atmosphere would only be active at perihelion, and we had a perihelion passage, I think, in the 90s or early 90s, and the question was, by the time we went out there, will Pluto move far enough away from the sun that the atmosphere would have collapsed? And the answer is it didn't, but Pluto is a very eccentric orbit, and it may ultimately collapse as it goes deeper or further away from the sun. So during part of its seasons, the atmosphere may be frozen out. And we certainly do have reservoirs of nitrogen in Sputnik Planitia, but the absolute escape rate, I know we have measured that, and so there is a number, and the number is consistent with continued existence of the atmosphere, but I regret that my knowledge escapes. I cannot tell you the physical processes, escape mechanisms, and how well those work, and if that's what's expected. My apologies for that.
But thank you. Neat.
Brian, I did see your hand up, and I will let everybody else go if they have other appointments to keep. But Todd can stick around and answer a couple more questions and hopefully pull up that one image if you'd like.
Yeah, let's see. So right now I'm not sharing anything, and I think what I'm going to do is, let's see, kill my PowerPoint and kill some of these other things. So I have Zoom going on here. Let's see what I had here. Okay, that's okay. Oh, I didn't kill these. Okay. Yeah, I think preview just may have gotten overwhelmed here.
Well, I don't think everybody uses preview to like try to show 64 megapixel images. And
You think that might be an issue, do you? Okay. Okay, let's see here. Yeah, my apologies for not having practiced this. Okay, let's try this. Okay.
if any of you have questions in the meantime, just feel
Yeah,
free.
go ahead. Go ahead. Now I'm
Yeah,
making
if it wouldn't distract you too much. Yeah, so for the Arrokoth object, so you just briefly said something about what's up with the neck between the two spheres. It was this sort of white. What's the thinking there?
Well, so that's the junction of the two lobes clearly. And the first thing is just the bare fact that it exists, underscores the fact that the encounter between the two lobes had to be very, very, very gentle, probably only as slow as 2 meters a second impact velocity, if not smaller. And so its existence means, underscores the gentle merging of the two lobes. And so that, raised why, how were they brought together? What is the physical mechanism? And there's still quite a bit of discussion about that. It is, and this is work that James Keen has done, who is an expert in the gravitational fields of, these irregular objects. It is the gravitational minimum. And so the question is, is stuff moved along on the surface and fallen into the neck and made it bright? And the other things we see, if you look closely at our best resolution images, you can also see that there's little dimples, which are also filled with white material. So we see, again, very compact depressions or local minimum, which are white. So the picture that there is some unknown material, and it is currently unknown, which has moved along to the surface and collected, explains that. So we have the potential is right. What the material is, I can't answer. Does that?
Yeah, that's cool. So it's dust bunnies or something. Yeah.
Yeah, dust bunnies might be just about right.
Oh, really? I was kidding. Yes.
Well, God knows, I don't know this stuff.
So
I have to say, this has been, I came into the team because my interest in image processing, and it's my own technical specialty, but I've spent the last 5 years learning geology, but I can only pretend to be a planetary scientist for a few rounds of questions before I completely show my ignorance with these things. But I've been trying to pick this stuff up.
no, that's great. And when the two, forgive me, but just one more, because I'm
No,
intrigued
sure.
by these guys, when they merged, is the thinking that they just stuck immediately, or were they kind of grinding against each other and then finally came to rest?
Well, I have wondered this myself as well, and that reminds me, something I have been trying to figure out is, what did that look like? And, can you find evidence of perhaps a previous contact? And I don't know a good answer to that. It's something I've wanted to know myself, because in my mind, I think I do see some features where I think I see a pattern on one lobe that matches something somewhere else on the other lobe. And I, do wonder if they stuck together. There's no glue that
Right.
happens, and if the contact is very gentle and there is still, say, residual momentum in one direction, I mean, does it roll around a little bit or something like that? Maybe not, because perhaps you expect them to be synchronously rotating at that point. But maybe the first point of contact wasn't the best place to be. Maybe there is a gradient that brings them together. It's a very good question. And I think that's something that, will slowly emerge as more people think about this. I should say with all this stuff, besides the team, there is a much larger community of planetary scientists who are very interested in these questions. And, we're only now, a year and a half past the encounters. So there's an awful lot of stuff yet to be shaken out. And I think this is one of them.
Cool. Thanks a lot.
But
So
so
go
that's
ahead.
something, because you are effectively describing features on Arakoth that line up potentially, and in some sense you're like Alfred Wegener, except instead of looking at South America and Africa, you're doing it on a completely different body in the solar system.
So Wegener, originally everybody thought he was nuts, and right, and I've read accounts of this. I mean, Bruce Murray in his autobiography said when he was a young graduate student, he looked at these and thought he saw evidence of supporting Wegener, and his advisor told him to knock it off. In my case on the team, I have certainly established more than once I'm nuts, and my trick here is sort of somebody new to the team who's come in more for technical reasons than brilliant expertise in planetary science. I think I have a ratio of I get so many brownie points for the image processing, and then I can cash them in for profoundly stupid questions about geology at some point. And I always try to stay in the black. But so do you see the do I have the image up? Okay, let's see if I can zoom this. This instantly, it did something I don't understand.
It just where your cursor was, so you just scroll up, I think.
Yeah, it zoomed. Let's see. Yeah, it's interesting. It zoomed once, and it's not responsive to any further zoom commands. But so this is, what can I show you here? I don't. Yes, I'm going to. Well, let's go a little further. So one of the things which is certainly interesting is, and again, not incredibly well understood, is the atmosphere has these layers in it, which we can track for a while. And all of this, let me just go over here. You can see these layers continuing around. And I think they may be gravity waves, but I'm not completely sure about that. There is one amazing feature here, though, which is just crazy, absolutely crazy. I couldn't believe this the first time I saw it. But do you see there is this cosmic ray that's that hit that is left in there. You see that bright spot next to the cursor?
Yep.
Do you see this dark wedge here?
Yep. It's a little posterized on Zoom, but yes.
Can you infer what that is?
Shadow?
It is the shadow. It is the shadow of nightfall on Pluto. I mean, we see this at dusk on the Earth, particularly if you're up in the mountains, the sun goes below the horizon and you can see the Earth's shadow, forming its pattern on the clouds. I remember I see it all the time when I'm flying an airplane. I cannot recall seeing this in any other planetary body. It must be there, but here you can see, there is night here on Pluto. Here the sun is still visible and is lighting up the haze. And it's just startling, this little goodie tucked away in here. So let's bring this around. One of the things which is I've come to appreciate that, is very big with people studying more the surfaces and properties are the properties of how these things light up with different phases. And so here the sun is just glancing across and you can see things that are very lit up. And this tells you that these, the properties here, if these are I think to do this, you have to be smooth, you know, perhaps with large crystals, but it tells you something about the material sitting in the bottom of these depressions. This is fun just because it's an oblique view and you can see the relief without use of 3D. You know, these distant mountain ranges, the bright sky makes it somehow more familiar. Again, phase effects. Here's the bottom of Sputnik Planitia. Here, with this phase right here, it looks very, very rough. Again, I know when I look above it with Laurie, this looks very smooth. So put the pieces together, you're learning something here. Now, something I don't know if you can see here. This is tricky. I can see it on my screen. Let me see. I think I'm just going to adjust the brightness of my laptop. Yeah, if the brightness of your laptops are turned down, you may want to adjust this. But you can see the haze here at a very low level. Can you see these little streaks here?
Yes.
You see them, Gautam?
I do.
So what's going on there is this is a very, very low haze layer, which interacts with the topology of Pluto. And so you can actually see the sun coming across here. The sun lights up this side of the mountain casts, or the peak of the mountain casts these shadows. And it's, you know, what you might see in Tucson, the Catalina is casting shadows in a deck of fog. But to see this, you know, geological relief on Pluto casting shadows is, for me, just tremendous. Oh, and here you can see again with a different phase, there's this glacier flowing into Sputnik Planitia. Now you can see the flow patterns, even at this oblique angle, very, very clearly over here.
Are all the linear features above it just cosmic rays? Because they seem to be different sizes, but they seem to have.
No, some of them are cosmic rays. This one probably is here. These are stars.
Mhm.
And what's going on here is this was taken with our panoramic camera, which is the spacecraft motion was put in to track Pluto during the exposure. And this is close enough, the exposure long enough that Pluto drifted with respect to the stars. So the stars don't stay put, Pluto does with the appropriate tracking in the spacecraft. Good eyes. That's right. I forget you are, I remember that. You were a very avid photographer yourself, as I recall. I should say for anybody who's interested, all of this material is publicly available. You go to the APL New Horizons website, you can find it, you know, in 10 seconds of Google. Anything I showed here, you know, you can grab and get for yourself. So I think that's about it. Do we have anybody else last licks?
I had a question about Aircoth, and was it chosen for a flyby because it was different in some way? Was it highly variable or something that should we expect most objects to look like this, or is it just a dumb luck chance, or was it actually chosen in a way that would cause it to be seen, right? That you see this double lobe.
Well, the glib answer is it's chosen because it was the only thing we could go to. So what we did was, you know, the whole mission was dedicated to getting to Pluto, and you know, the flyby was paramount, and the mission, in its requirements and the description, you know, said, and we hope to get a different, we hope to see a Kuiper Belt object undetermined after the Pluto encounter. There was a ground-based effort using mosaic imagers on large telescopes such as Subaru to find an object from the ground in advancing the encounter is very, very difficult because you're looking right against the Milky Way where you have to be nuts to go look for a faint object. And unfortunately, you know, although we discovered lots of new Kuiper Belt objects, we did not find anyone that we could go to. So there was a Hail Mary pass, which was to use Space Telescope. Space Telescope produced two objects with a lot of searching that we could go to. One required us to exhaust nearly all of our fuel, and we didn't want to do that. And so we took the one with the more modest delta V. So something you could discover with appropriate delta V is the primary criterion or criteria, and then everything else falls into place after that. Now, we did think that this was representative of the cold classicals. The orbit was right for cold classical, low eccentricity, nearly circular, low inclination. We knew that the colors, which were very reddish, was again typical of the cold classical. We know that cold classicals were preferentially are at least 50-50 binaries, and that's with discretely discovered companion satellites. We don't know closer in. So we didn't see a satellite of Arrokoth, but we did have occultation data. Now this is after we had dedicated this to being our target. Occultation data did show that it was bilobed, or two closely bound satellites just happened to be overlapping. We didn't know which one it was. Now there are some selection effects. One of the things which is interesting is that on the way in, we saw no light curve. We tried very, very hard for a light curve. I was part of that effort, and we did not see any photometric variations we could believe. And the answer was because it was rotating face on to us, our approach vector, so not being modulated. But the member of the team later said, well, that's what you'd expect because it's right at the edge of what we could see with Space Telescope. And if there were large modulations in its brightness, we may not have detected it, would be very unlikely to have detected it with Space Telescope. So small object face on gave the best possibility of detection. So that may be a bias. It is a problem that, we, have a sample of one, but so far, everything, and the way it is said, it's a strange object, but we hope it's typical.
Yeah, exactly. Yeah.
And that's the best guess it is that it is. I mean, there were theories by David Nisworny of exactly how you'd form these things, and it produces a bilobed object. Well, not bilobed object, but it produces a bound binary. That was extant theories going in that these things were commonly created. So far, there is nothing to take us away from the fact that we think that, yes, this is representative. But, what are you going to do? We'd like to get more. We are looking for more objects. It is not likely that we will find one that we can encounter. We do have fuel left over, some delta V budget, if it's close enough. I say it's probably 1% chance we can find something, but yeah, you'd like to go get more. But I think as far as we can tell, there's nothing that has said this is very different from anything else out there.
Well, if we don't have any other questions, let's.
Well, quickly along the lines, what's next? So when do you leave the heliosphere? Must be pretty soon.
Oh no, I don't think so. The heliosphere with Voyager, I think they encountered about 100 AU ballpark.
Yeah,
past it.
You guys are going at a good clip, though.
We're going at a good clip. We're not going as fast as the Voyagers, though.
Okay.
And right now we're not quite at 50 AU.
Okay. Okay.
And that's taken us, 14 years to get there.
All right.
So, and the best guess is, we can probably make 85 AU. One of the engineers who's really looking at this thinks that he can get us to 100. We're going in the same direction of the Voyager's ballpark, which is down the Helia tail. A different spacecraft in a different direction might encounter the heliopause earlier, but I regret, unless solar activity goes way, way down, or something anomalous like that, I don't think that the mission will survive to actually see the transition that the Voyagers saw.
Fair enough. All right.
So let's thank our speaker again for an entertaining talk. That was great. And I'll let you all go. But then after I let everybody go, I'm going to ask you one last question, Todd, which has to do with your background wallpaper. The left panel on the Pan Am flight in 2001 on the top, why does that left panel have random variable starlight curves?
I wish I could ask Stanley Kubrick. I know who I could ask. I went to this 3-hour lecture. God, Douglas Trumbull. Yeah. They got him to be, he was the one who, as a young guy, did the special effects for 2001. And they got him to be on the board of directors for Stewart Observatory. And this was, I don't know, maybe a decade or more ago. And he gave this talk, and he would take all the questions that you wanted. And I left after a few hours. I'm a nut for 2001, but I got saturated at some point. But it was an incredible experience because he showed these black and white stills he took of this, and he said, "This is what I did to make this effect." And I was like, "Oh my God!" This was like I was just completely geeking out. And here's this guy that made all of this work, and the part that blew me away, and this goes back, yes, it had to be in the later part of last decade. You may remember, or maybe you didn't, I was attempting to PI one of the early JDEM concepts.
Yeah.
And one of the things that we wanted to do to calibrate it was to calibrate the whole telescope. We wanted the best photometric calibration we could get. And the only solution was to put the whole instrument in a light box. I mean, the whole telescope, which was kind of an extravagant solution, and we didn't get that far to see if that would fly. But anyway, with that background, Douglas Trumbull was talking about how we did the conference on the moon scene. And you may remember that, Haywood Floyd is lecturing everybody, and they're in this conference room that has these glowing white walls, which are perfectly uniform. And Kubrick demanded that they be perfectly uniform. And I couldn't believe what they did. What they did was they built the set of the conference room in a giant light box. And on the top of the ceiling, so you see there, it's a room and there's a ceiling. On top of that was this huge, immense array of photo floods, which were shining out to the outer walls of the light box, which diffused and reflected back into, the conference room with those translucent screens. And it just blew. I mean, first of all, you can imagine for old high, color film, the sheer wattage, the power plant it would take to light that up. And I've seen pictures of it. It was like unbelievable amount of lighting. And to get enough light to diffuse through and then light up the scene so they could film the actors, and he just described this and more. So, I should say, I don't know him to ask him, but at least there are still some people around that might be able to answer that question.
Cool.
All I can say is that when I was a kid, watching that scene, the Pan Am Clipper, it looks so sophisticated, with all those graphics, and now it looks so archaic. In fact, you can tell me to shut up. The thing that blew me away more than anything, the effects of 2001, and this just made my jaw drop. You may remember they're on the Discovery, and they're going to go out and service the antenna, and they ask Hal to display this. And at that scene, there's a white on blue wireframe graphic that comes up that shows the antenna rotating around and gimbaling. And you look at that and say, yeah, wireframe graphics, that, they were able to do that back then, just barely, and you don't think much more about it, except you may laugh a little bit. Yeah, nobody does wireframe graphics anymore like that, but, it looked pretty good in 2001. Well, in the 60s, that was ahead of them. They had wireframe graphics, but they couldn't do it. And so what they did was they made a wire model, which they painted white and filmed rotating. It was a mechanical model. And I just like, my God, wireframe graphics were so fancy back then to fake them.
Yeah.
you built a physical model and pretended it was wireframe graphics. We're now we've completely given up modeling altogether in science fiction movies and make graphics for every, completely 180 degrees around.
Well,
On that note,
thank you so much for this talk again. This was great. I'm going to put the recording up probably within the next day or two. I'll send you a link.
okay.
As always, thanks, Sod.
Okay, thanks for the invitation. This was fun, Gotham, and take care.
Absolutely. Bye.